In this video, we're going to show you how to calculate the curl of a vector field in 2 dimensions using the ComFiT library. And so to begin with, I have already installed ComFiT here. And then I'm going to import the necessary packages, which is ComFiT, NumPy, and SciPy for Fourier transformation. And the test vector field that we're going to be computing the curl of is this vector field here, g of x and y, which is it's essentially this y minus the middle part as the x component, and x minus the middle x coordinate as the y component. These y mid and x mid are properties of the instance of this system here. So I'm initializing an instance of the base system class with dimension 2, and then y mid is the mid position. You can see it here, it's 50, and x mid is the mid position in the x direction. And in order to make the dimensions, so this NP array, this array here should have the x component of the vector field as the first component, and in order to get the dimensions to line up, I need to have add just 0 times this is x variable as well, because this sys_y variable here, you can see it has the shape of 1 times 101, which is the dimension in the y direction, and then this x component here has 101, 1. So when I add them together, I get something which has 101 times 101. So anyway, that's the x component, and then the y component is this, x minus x mid. And then outside of this vector field, I have this Gaussian function here, which essentially just smooths the field around the middle part. So it's a function that calculates a Gaussian function which smooths the fields out so that it's still consistent with the periodic boundary conditions that is required. And it has a parameter width which just tells how big that Gaussian should be. But if we just I can probably, just to show you how this Gaussian field looks. So if I just take this Gaussian field here and I plot it, you can see that it's just like this Gaussian function here, which sort of makes sure that it's 0 at the edges, which means that whatever this vector field here is, it's going to be something in the middle, and then it's going to go to 0 towards the edges. So I'm going to remove that, and then we're going to have a look at what this vector field looks like. So you can see it has this spirally behavior, right? This vector field here. Now, to calculate the curl of that vector field, we need to know what the curl is. And the definition of the curl is something that exists in 3 dimensions, really. And it has 3 components. It has the x, y, and z component, where you have the derivative of gz, the z component with respect to y, the derivative of the y component with respect to c, and so forth. It's just that now, since we have a 2-dimensional vector field, gz is just 0, and it doesn't make sense to differentiate with respect to the z variable. So the only component really of this curl that is interesting is this third component, which is the derivative of the y component with respect to x, and the derivative of the x component with respect to y. So let's just start calculating those. So the first thing I need is the derivative of the y component with respect to x. And so first I need to get the Fourier transform of the g field of the y components. So f of t n g of 1, that's the y component of the field. And then I need to, in Fourier space, I need to multiply that with the differential operator, which I went through in the video on how to calculate derivatives with ComFiT. And then I need to take the inverse Fourier transform of that to get it back to real space, which turns into this. And then, of course, since I know that this is a real field, I don't want to keep any imaginary component of the field. So I'm just going to take the real part as I know that it should be real. And then I'm going to do this exact same thing to calculate the y derivative of the x component. Then I'm going to take the y derivative and differentiate with respect to the x component of the field. And so the curl, the z component of the curl then is given by curls is given by dx gy minus dy gx. And okay, it's done there. So let's plot it. Curl z. So let's have a look at it. And you can see that the curl of this vector field here, it's 0 at the edges, where the well, it's not 0 actually. It's actually a negative, and that has to do with the fact that the Gaussian function is sort of killing the vector field as we move towards the edges, and that gives like a slight positive contribution. But here it's no, that's wrong actually. It is actually 0 at the edges. So it is 0 at the edges, and then it's slightly negative here as the Gaussian is sort of killed. And then you can see the curl of the vector field here, and you see that it has a strong positive curl near the center, which sort of goes away as you move towards the edges. I remember the way that I learned curl back in the days was to imagine a mosquito that has lost that is sort of unconsciously flying around in the wind, and if the mosquito is rotating around its own axis, then there is a non-zero curl in that place. So you can see, if you imagine a mosquito flying around in this field, you can imagine that as it gets close to the center, it's sort of swirling around its own edge, which is why you have a positive curl here. And it also explains why you have a negative curl in this area, because in this region, if you placed your unconscious mosquito in this region, then it would actually start to rotate the other way around, because it's sort of feeling the pull on this left-hand side here. So that is how you calculate the curl of a two-dimensional vector field using ComFiT.